please give it up for Boyd Multerer.
Thank you much. Hi, I'm Boyd, and I'm your designated nerd for this event. Let's see, yeah, everything he said is true. I spent 15 years on the Xbox team, and I got to do three things there. I got to start Xbox Live. It was once upon a time, the whole team was just me. I got to hire all the engineers, participate in the design of it, and worked on that for 4 years. And then XNA, which became the developer program. He said, think of it like the Unity for consoles, but if you've used Unity, you know that you're writing in C#, and that's because we chose C# and XNA. And then the last 5 years I was on Xbox, I ran the operating system team for the Xbox One console. That was really hard, right? That was 5 years of slogging through, and especially the last year, there were 300 of us who were there 7 days a week for the last 6 months, and we were really tired at the end. So after that, this is about 3.5 years ago, I and a whole bunch of other people, we all left, and it took me at least a year to recover from it. We could do a talk about burnout and about recovery and all that. You have to take the time, you have to take care of yourself. The year after that, I spent exploring, well, how does the rest of the world write software? I wanted to write different things and explore and do it without using the tools that I was used to at Microsoft. So I looked at all the different languages and different ways of building services. And then in the last year and a half, I really finally focused in on what I wanted to build, and I've been writing code solid. So that's pretty much what I do all day long. I'm sitting there in my office at home, and I'm writing code like crazy. And we'll talk a little about that. But today, what I want to talk about is there's hard problems that we had to solve in building a console. And there's lessons that you learn along the way. And anytime you start a new project, it's important to think about the trends that are happening that you have nothing to do with. What are the things that are happening whether or not you do anything? Because those are either going to be things that run you over, or you can grab onto it and get a ride. Right? And one of the ways you do this, one of the ways you understand these trends is you can look for places where the tools and the procedures that you use are exaggerated. Yesterday we had an astronaut on stage, and that's a great example of exaggerated engineering. Building a rocket is really, really hard, and they had to solve problems that had never been encountered before. But now, years later, many of the things that they did are in our everyday lives, affecting everything from the way cars are built to the way pens are that we write. The same is true in software. You can look for places where engineering and the problems that you have are exaggerated, and they can give you clues as to what are the things that are coming for the rest of the tech industry. Gaming in particular is an exaggerated sort of field. When normal engineers write software, you work in a tool called Git to check things in and out, and you may have 10 people writing code working together, and your total database of all your code could be tens of megabytes, maybe 100 megabytes. In a game, you've got 1 to 10,000 artists working at the same time, and your database is 30 to 40 terabytes. And these exaggerations cause everything from networking problems to interaction problems, and they give you hints as to what's coming. So this is largely what I'm going to talk about today. Now, my goal is not to make anybody in this room an expert in any of the technical things I'm going to talk about. We're going to go through a whole bunch of topics really fast, and I'm not going to try to teach you anything in depth about any of them. But the goal is, in the next couple years, I don't know if it's going to be 1 year, 2 years, or 10 years, but in that kind of range, at least a bunch of these things are going to become real problems. Now, if you're in marketing, the goal is you should remember this talk 5 years from now as the engineers are busy talking about whatever, and you'll go, oh, do you mean this? And they'll all look at you and go, how do you know about that? Right? I want to give you the words to use and at least the topics to be talking about. If you're in engineering, my goal is, all right, when you encounter this problem in 3 years, you have a starting place to where to start your research. Okay, so we're going to do this by talking about three subject areas. It's going to be devices, the environment that these devices live in, and software. So let's start with devices. I think there's two kinds of devices in the world. And this is an ironic picture because it shows three, and they're all in the first category. All right, there's two kinds of devices in the world. There are general purpose devices. This is your phone. This is your laptop. This is the computers that we're used to using. When these computers are made, the people who make them a computer have no idea what software you're putting on it. Right? You might put a game on your phone. You might put a spreadsheet on your phone. You might use email on your phone. You might be printing. You might have all kinds of things running on your laptop, and the laptop manufacturer has no idea in advance. The other kind of computer is a single-purpose computer. At the time the computer's made, you know exactly what it's for. It's only going to run one program ever, or one class of programs. A console, a gaming console, fits in that category. It's only built to run games. And you're not trying to make it good at running printer drivers. You're not trying to make it a good web server. You're trying to make it good at games. So you make different choices. Right? So those are the two categories. I'm mostly going to be talking about the single-purpose computers. You may have heard of IoT. Those are single-purpose computers. I personally don't like that name. So I will say connected devices or single-purpose devices, and that's kind of what I mean. All right, let's dive into it. We're going to start the roller coaster here. The first area we'll talk about is efficiency. In a gaming machine, well, let's back up. On a laptop, when you're running your laptop, and the laptop that's running this presentation, it's sitting there around 5% usage. Most of the time, it's not being used because it needs to reserve space and conserve power because it doesn't know if I'm going to try to print something. It doesn't know if there's a web server running. On a gaming machine, if it's not running 100% all the time, someone made a mistake. Right? So the idea is, when a gamer buys a game machine, they're putting out money for this computer, and they really want the most performance for the money they spent. Right? So the game developer really wants to use all that power all the time. And that's why you get more performance for your dollar, for your money, on a game machine than you do on a general purpose machine. When you think about devices, and this could be a sensor on a valve, it could be something measuring your power, it's the same kind of idea. You know what it's going to be used for, so you pick the smallest computer you can pick that still gets that job done. Right? So you have to flip how you think about choosing the computer to the software instead of the other way around. An example would be Nintendo. They choose in advance, they choose the games they want to write, and then they pick the smallest console that will still play those games. So you spend the least amount of money to still play the games they want. Who's heard of Moore's Law? Yeah, that's about what I expected. All right. Moore's Law, Gordon Moore was one of the founders of Intel and one of the creators of the modern chip architecture. His rule that he made was that every 2 years, roughly every 2 years, the number of transistors per square millimeter will double. Okay, the implication is a transistor is the smallest unit of compute in a computer. Basically, it's like a light switch. You can flip it on or off, and that means electricity can go on or off through it. And you can hook them up into big, complex patterns, and those patterns will do things like add two numbers, or subtract, or multiply, or divide. You get enough of those patterns, and you have a CPU. You have a computer chip. That's all they are. It's just patterns of transistors. Through the 80s and the 90s, these patterns got bigger and more complex as they were able to put more transistors into the same space, so the transistors got smaller. A funny thing happened around 2010. The patterns had gotten so big and so complex that it wasn't really worth it anymore to make them bigger. So the CPUs stopped getting more complicated. They stopped getting more complex. And instead, the next time that it doubled, instead of making a bigger CPU, they put two of them down, two of the same thing. So now when you buy a PC, it says how many cores it has, like 2 cores or 4 cores. 4s are pretty common right now. That's literally what it is. It's just 2 copies of the CPU. Right? If I was going to go get a brand new Mac Pro right now, which I would really like to do, I've noticed I can get a 12-core computer. That's crazy. So in a GPU, the graphics processing unit, same thing. I've been fascinated by this TV as I've been watching it. The screen is amazing. There's all these little squares. Each square is a segment of the TV, and they're put together in this array. I'm a nerd, by the way. And have you noticed that this block over here has been darker, and this section is a slightly different color? And the whole time, at the first talk, I thought, oh, wow, he kind of put that into his slide deck. That's really cool. And then the same thing on the second deck, and I'm like, oh, it's the controllers behind the screen. A GPU kind of works the same way. There might be 200 to 400 processors in the GPU in your computer. Each one's really little, and each one is responsible for drawing just one square. And that's how they can draw the screen really quickly. But it means that you have to learn how to program so that your program is running on lots of computers at the same time, and then it all comes together. It's very different from how we were trained. By the way, the red stuff is sort of the predictions, the things that we have to do. So we're going to have to get good at parallel programming, because this isn't going away. And as we talk about IoT devices, the speed of the device might stay the same, but the chip's going to get smaller and less expensive and use less power, because you're choosing to go for the software. Security. We're going to come back to security a couple times. In a normal general purpose computer, the way you think about security is someone bought my computer and they're running their web browser or they're running a spreadsheet, and my job is to protect you against an unknown attacker that's sitting somewhere else. In a game console, the job is that the person who owns the console is working with the attacker who has a soldering iron, and they're trying to attack the board in order to play free games or to cheat on the games. Right? It's a completely different problem. Most software people have been trained on the first one, but not the second one. And even the hardware people think about the first one, not the second one. As you think about devices, if you're an electrical company or a gas company or anyone who's putting devices into the field, you have to assume that somebody has taken one of those devices, opened it up, and used a soldering iron on it, and how is that going to affect the data you're getting? You have to think like a console maker. It's a very different attack scenario. Whoops, what did I do? Hit the wrong button. How do I get it back? Thank you. Okay, let's talk about the environment that these computers live in. The first here is that these machines are always connected. So in a game console, any modern game console now, you turn it on, and while you could run it offline, it's much better if you run it online. So think of it as the machine turns on, you're playing the game, and it has opened up a connection to a server, which is way over there. And the person you want to play with has also opened a connection to that server. And that's how you find each other. That's how you know who your friends are, who's online, what game they're playing, how you invite them. Twitter and Facebook work the same way. You've got a long-term connection to a server, and that thing is what routes the information, the tweets, the social media, all that stuff. It's really hard to build, right? Those servers can only handle so many connections at a time. And in the old days, like when we were first building Xbox Live, you cross your fingers and you could hope you get a couple thousand connections per server. Maybe 10,000 if on a good day. Okay, well, if you have 10 million machines that are online, how many servers do you have to put together just to support all those connections? And how do they talk to each other? It gets really expensive and really hard. But there are new modern techniques for how you go about building these. My personal favorite right now is Phoenix, written in Elixir on Erlang for the nerds. And you can get the number of connections to those devices much higher than about 10,000. I've seen some up toward 2 million. This is a topic that will be coming, and anyone who's thinking about building devices that are connected, you're going to hear about this, and you're going to have to think hard about it. Latency. I told you, we're going to cover a lot of subjects here. Who knows what latency is? Okay, a couple of hands. When you buy your telecommunication package, when you talk to your telephone provider, when you're buying your internet package, they sell you bandwidth. Bandwidth is how many bits can you send at once? What's the size of the pipe you're getting? You know, how many megabits, how many gigabits, that kind of thing. But just as important, and maybe more important for some types of applications, is the latency. When I say latency, if I say something and it goes to that corner of the room to that guy, and then if he waved and that signal came back to me and I saw it, how long did that take? Right? I said it, went to him, he raised his hand, and I saw that signal come back. That's the round-trip latency, is that time. When I'm playing a game like a Street Fighter or something like that, I push a button, that causes an animation to happen. That signal goes out to the server, it comes back to the other person's machine, they see it on their screen, they push a button, animation starts, goes out to that server, and it comes back to me, and I can react. That's the total latency. Fighting games are latency sensitive. If that time gets above 30 milliseconds, you can't play the game anymore. It doesn't work. In a racing game, it's less sensitive. If it goes over 60 or 70 milliseconds, you're still good, maybe 100 milliseconds. Above that, the cars are in the wrong spot. You think you're going here and it's an empty piece of road, but no, there's actually BMW there, but you just don't know it yet. That kind of thing. As you think about non-gaming scenarios, what if I have a gas network, a natural gas network, and I've got sensors all over the city, and I'm measuring the pressure as it changes, and I have a computer somewhere that's going to measure those changes and then open and close valves to keep the pressures the same. If that signal takes 2 seconds to get across the network to this machine, and then the signal takes 2 more seconds to get back, there may already be an explosion somewhere. Right? Latency matters for some applications and not for others. For example, the game of chess. I don't think anyone's going to care if you see the other person's chess move a second later. It doesn't matter. Right? So you have to think about your application, and you might need to be talking about latency. I did it again. Help. Okay. Right, I keep pushing the wrong button. Security. Now, in the sense of the environment you're in, there are security with regard to explicit technical attacks. Someone's trying to hack your machine. But there's also behavioral attacks. In gaming, there was a phenomenon where I'd be playing a game against somebody, and I'm losing. You're clearly winning. And what do? I reach out, and I grab the plug, and I pull it out of the wall. I'm sorry, my network went down. I couldn't finish the game. You don't get the win, and I don't get the loss. Right? And it didn't break any rules, and it wasn't a technical attack. What do? Well, you have to keep track of it, keep score somewhere. And if it happens again to the same person, all right, this is starting to get kind of weird. Maybe they have a bad connection. If it happens again while they're at someone else's house, no, this is a behavioral problem. Right? This is where machine learning comes in. Right? How do you look for non-technical attacks and understand that those are happening, and then either say, no, you don't get to play those games anymore, or you take other actions. And this could be for any other type of device that's in the field. Pressing the right button. Let's talk about software. All right. Longevity. This is something that's a little harder to wrap your head around, but it's really important. Think about games for a second. They say something about who we are. They say something about who we were. These are ways of capturing what our society cares about right now. And let's say I've got a game that played on the first Xbox, and it said, I don't know, whatever you want to say, and some future archaeologist wants to examine it and try to figure out what was going on at the time. How do they play it? Well, they have to find a working original Xbox. They haven't been made for years now. But they're all cryptographically signed. They're all locked down because they didn't want to have the cheating, and they didn't want to have the piracy. Can we still play these games? Another actual example is in the gaming world, you'll frequently see it so that where studios form to make a game, they'll get funded by a big publisher, money comes in, they spend 2 years, they write the game, and the moment the game ships, the company goes out of business because it was only formed to make that one game. The people who wrote the game are gone. It's now 1.5 years later, and there's a critical bug, and it needs to get fixed. Who do you talk to? I don't know. This is a real problem. Now let's change that scenario a little. We're talking about the future. We're talking about connected devices. You're a construction company, and you've just bought a brand new cement truck. All right? You've just bought a brand new cement truck. It's got a computer on it, and I'm not kidding. I went to this thing in Las Vegas called Con Expo, Construction Expo. It was a crazy event. And had cement trucks, everything from cement trucks to the giant cranes they built the skyscrapers with. Every single thing had a computer on it. So you've just spent €250,000 on this cement truck. It's got a computer that drives how fast it's turning and how much water is going in. And you're using it, and it's great. But it talks to a server that's somewhere in the cloud to keep the truck configured right. The company that made the truck goes out of business. Can you still use your €250,000 truck? Today, that's unclear. You don't know. I think that's a problem. as we think about software, as we think about these devices and how they're deployed, how do we know that the money that we spent is going into a scenario, into a device that has a life that might live beyond the company that made it? Can the truck have enough brains, have enough smarts inside of itself to continue to run its own configuration software? Right? That's longevity. And this is also hard to do. So it's partly about preserving what was, and it's partly about preserving what we purchased beyond the life of any one company. So we have to think about device self-reliance and the containers that it runs in. I'm going too fast. Robustness. This is a hard one. Most software engineers have been trained for speed. They've been trained to write software that's performant, or actually, these days, they've been trained to hack together lots of pieces of JavaScript into just something that works. But we don't talk about robustness. Errors happen. Software bugs happen. Mistakes happen. You can't. There's very little software that doesn't have any bugs in it. There's some exceptions, which I'm not going to go into. Let's just assume that every single device that you've purchased has got a bug in it somewhere. You really want to make sure that as you're driving your car down the road, every time you use the brakes, it's not eventually going to cause a memory outage scenario where your power steering goes down. That would be a bad thing. You don't want the sensor on some critical piece of equipment that starts to fail, the sensor starts to fail, putting bad data into the system, which then later causes something else to stop working. So we have to think about our software in ways where you package even a single program into pieces, where any one of the pieces can fail and can restart itself, so that the software package is able to heal and is able to keep running even under adverse scenarios. So if you've ever played a game on a console, how many times have you had to run check disk? Never. Right? As you think about devices, these are things that don't get configured, and they don't get maintained. And you can't ask the owner of the device to run software on it once in a while to maintain it, because they're not there. It's off hanging in a tree somewhere, or off a pole, or it's out in the field. So you have to design your software so it knows how to recover itself. Let's see. So partly the two things here are you have to separate the functionality into pieces that know how to recover themselves, and then you have to assume that they are going to fail. My current favorite, for the nerds, my current favorite piece of technology for this is Erlang and OTP. This is actually really old stuff. It was started in the 80s. But when you send a text message, when you call someone on your phone, it's probably going through an Erlang server. And it was designed where one phone call failing doesn't cause all the phone calls to fail. Right, so they had the same philosophy, and there's a bunch of tools that they've built up which are super applicable to connected devices. Software management. Okay, if you have an iPhone or if you have an Android device, how do you put apps on it? You go to the App Store, you find the app you want, and you trust that it's a working device, it's going to be a working application. You trust that it's not malicious because you hope that the people at Apple have done a good review of the application, and they've cryptographically signed it so it can't be modified. And that the fact that they allowed it into the store means there's some goodness. All right, same thing goes for consoles. There's just a centralized control, right? A centralized control of that application management. On the case of your PC, especially the older ones, you load the software on yourself. Right, the user has control. You can put any software you want on that thing and you can run it. When you think about devices and connected devices and the networks that they run in, it's somewhere in the middle. You want the centralized control because you don't want any random thing running on it. But each company that's maintaining a network of devices, they want to know that it's only running the stuff they've chosen. They want to do their own verification. So we have to find a middle ground where there's application management systems that can be broken out into their own little bubbles. Right? Think of it as, I've spent some time talking to utilities. Like there's a utilities I talk to that distribute natural gas. And they have these trucks that go out in the field to fix leaks. Maybe they have 1,000 crews. They're out in the field. They're dealing with equipment. They're dealing with tools. They're dealing with valves. And they want to maintain it. And they would love to get data from all this stuff at the central office. So what did? They gave every single person an iPhone. And then they said, put this app on the iPhone and please open it at the start of the day. How often do they remember to open it? How do you know that the game that they put on the phone isn't interfering with it? How do you know that all the other stuff the phone is doing is not going to get in the way of the app that you want to run? You don't have guarantees. What they would really like is to say, here's a device, I'll put one on every truck, and I know exactly what's on it, and it will only run the stuff that I chose, and different gas companies may choose different things. Right, so that's kind of what I mean by segregated, distributed management. Okay, we're getting back to security. Security is a hard enough subject that you can go into any one of the areas and you can dive deep into it. So in this case, this is probably the biggest one that I've had to wrap my head around lately. We have a problem in software. The model that almost every single operating system that we use was designed in the 80s. It's called a macro kernel. So how many people have bought a new printer, and the first thing you've had to do is install a driver for the printer? Right? I know I've had to do that. What's happening? When you buy that new device and you have to put the driver in, the computer has been segregated into these different regions. In the old days, you had an application running on your computer. If it crashed, the whole thing crashed. You had to reboot the whole computer. So then they created something called user mode, and they put that application into a sandbox. So if it crashed, just the app crashed, not the whole computer. And that worked, except it was too slow. If the app needed to talk to the hardware, it had to cross a boundary and talk to that physical layer, and that was really, really, really slow. So what they said was, okay, let's take the software that talks to the hardware, and let's call that a driver. And that gets loaded into what's called the kernel, which sits below the application. The kernel is privileged. The kernel can do anything. It can see all the memory. It has permission to do anything on the machine, and it can talk very quickly to hardware. When you bought that printer and you installed that driver, you're installing someone else's code into the most privileged part of your computer. It can see and do anything. So companies like Apple or Microsoft or whoever, as they're building these operating systems, they have to worry not just about their own code. They have to worry about all the third-party drivers that are getting loaded into the most secure portion as well. And it's been working okay so far. But part of what you learn building a game console is you get this third-party code coming from all over the place. You cannot check it all for security errors. Right? I've come to believe that macrokernels, this includes all of them, every single major operating system that we use, I don't think they're viable 10 years in. Right? Because the third-party driver model is just unsecurable. Now, these were issues that they chose this design because it was needed to run computers in the 80s. It's now, let's see, by the last time I looked, it's 2018. Computers, because of Moore's law, have gotten a lot faster. We've gotten a lot better at managing that transition. We don't have those original problems that we had anymore. So there are other designs, which are much more recent, they were developed in the 90s, called microkernels, where each driver also goes into its own little protected bubble. So, by the way, as I talk about this stuff, I don't expect you to remember it. My hope here is that if you're in PR, if you're in marketing, you're thinking about social media, 6 years from now, there's going to be some massive hack that causes the hospitals to have to reboot all their computers because all their hard drives have been encrypted. Wait, no, that was a year ago. There's going to be some massive hack that gets everybody all worried. And they're like, oh my gosh, there's all these third-party drivers and we don't know what to do about it. And you're going to say, have you thought about microkernels? And the people you're working with are going to go, oh, good point. I'll have to go look at that. Right? That's why I'm trying to explain this. I know this is a hard concept, but microkernels offers a way out of the problem that we're in. It's just really hard. right? And it's going to take time for people to develop it. But if we start asking for it and we start pushing for it, sooner or later, we're going to have to go down that road. Okay. So it's been 3.5 years since I left. So I'll talk a little bit about what am I doing based on these predictions. I spent a long time just trying to understand what are the problems that we face and what are we trying to do. And then, another year researching and trying to decide, well, what can I do to help? Since these are all things that are happening anyway, how do I fit into this world? So I haven't talked about this, by the way, to anybody yet. So you guys are the first who are going to get to see this, but I'm starting a company, calling it Crichton. And I like the bird. And my mission, what I'm trying to do, is to I'm going to start by creating an application model. This is aimed at single-purpose devices. So if you're building an application that's going to be running on, I'm not trying to compete with Apple or anyone like that. I'm not trying to talk about general-purpose computers. When I first talked about building effectively an operating system, some of my friends were like, you can't compete against those guys. I'm like, I know, I'm not trying to. Right, so you talk about an application that's if you're talking about applications that go on single-purpose computers, they need to be robust. I want them to live beyond the company that made it, and I want that UI to be used remotely. Meaning, I got that cement truck, the company's gone out of business, I want it to be relatively easy for me to put my own server up, bounce the UI off onto it so I can control the truck from remote. And this is what I've been writing code on for the last 1.5 years, and I'm about to release some software later in the summer. In the future, my goal is to work on next-gen security. And I'm not going to say exactly what that means, but you can probably guess from the 3 different security slides I talked about. Right? These are issues that we're going to have. They're really hard. I don't expect to have anything done on this subject area for at least 2 years. But these are things we have to start thinking about now in order to put ourselves in a position where we're ready for the events that are going to happen. All right, let's have a conversation. Let's talk.